All right, today we are going to switch gears. We are going to take a look at exponential functions. Exponential functions are probably one of the ones that if you've encountered things before, this one you might not have. However, it's super applicable, and you see applications of this every day, or at least nearly so. And so we are going to do some application problems in this so that you can see how these are used, because they really are used all the time in your life. You just didn't know that that's what they were called. So to start with, an exponential function is an equation that has the form y equals a times b, and b is raised to the power of x. There are some conditions on that. The conditions are all about the base of the exponent. The base has to be positive, and it can't be 1. And if you think about it, it kind of makes sense why that would have to be true. If it were negative, think about what happens when we raise negative numbers to powers. If it's raised to an even power, it becomes positive, and it's raised to an odd power, it stays negative. So if this were negative, you'd have some sort of bouncing around going on. That's less than desirable. And if the value were 1, what is 1 to the x? 1, and it would be a horizontal line. That's a line. That's not an exponential function. So if you have this form, you get one of two equations. One possibility is that your equation's graph, I should say, looks like this. And this is the graph that happens when the b value is bigger than 1. And the second possibility is that the graph looks like this. And this happens when the b value is between 0 and 1. Hopefully you notice that these two graphs are quite similar. All they really look like is a rotation around the y-axis, right? If you were flipping it over or I shouldn't say rotation, but a reflection. If you did a reflection over the y-axis, they would line up. A couple of features that you should notice that are common to both graphs. The first one is that they both have a horizontal asymptote. Where is their horizontal asymptote? At what? Good. It's at y equals 0, or the x-axis. So I didn't draw it in, but can you see here that this is approaching this line here in the middle? Yeah, there's a horizontal asymptote at y equals 0. They also both have the same y-intercept. You might have noticed that's how I started my graph. Where's their y-intercept? Zero, 1. You guys even said it in point form. Thank you so much. Yeah, the y-intercept is 0, 1. Cool stuff. So these are some features we're going to use as we draw graphs. In particular, we're going to have some equations where we have values, obviously, in place of the a's and the b's. The a value can be any number. It will affect, how narrow or how steep graphs is, or how flat they are. And it might affect if it flips over and flips down, like across the x-axis on the bottom. So if it were negative, it would do that. And so we're going to see one of those as well. Here's our first one, though. So this one has no a value at the beginning, or you could say a is 1. It just has a b value of 1/3. So we're going to fill in this chart. There's some of them that are very specifically going to ask you to fill in a chart of values. So I wanted you to see how to do that. But in other cases, we won't necessarily need 5 values to graph this thing or anything. Honestly, a couple of values is enough. 2 is really enough, 2 or 3. So how does this work? We're going to actually start in the middle of the list of numbers, because it's the easiest one to do. If I had 1/3 and I raised it to the power 0, what is anything to the 0 power? 1. It's a fact about exponents. So this is actually 1. And if you go down from there, we'll come back. I promise we'll get the ones at the top in a minute. What is 1/3 to the 1? 1/3. And then what is 1/3 squared? 1/9. Is everybody good with those values? So far, so good. And then we're going to go back up to the top. So we'll just go with the -1 next. 1/3 to the -1. So does anybody remember what happens when you have negative exponents? It flips it. So what will 1/3 become? 3. You got it. So I actually get a larger number than 1 on that one. And the last one, albeit the top one, has a -2. So I still flip it, but what will I also have to do when I flip it? Square it. And what is 3 squared then? 9. And you kind of might notice some symmetry in the graphs that you did, right? Like you start here in the middle, and then this one and this one are reciprocals of each other, right? And the top one and the bottom are reciprocals of each other. And that always happens, unless there's like a shift that moves it up and right, up and down, left and right, then that might not happen in those cases. But that is very common for these graphs. All right, so our second question then is to graph this. Quite literally, you can plot those points. You can also remember some of the features of what we just talked about. There's going to be an asymptote here. You don't necessarily have to mark it, but you better draw it like it's not going to cross. I mean, if you start crossing the axis, we're going to have problems. I do have the ordered pair 0, 1. It's in my table, and it's a fact about these graphs. They all have that, aside from being shifted up and down or left and right potentially. I had a value at 1, 3. And a value at was it 1, 3? No, it was at -1, 3, wasn't it? And a value at 1, 1/3. So those 3 points really are enough to graph this. I know which of these two shapes it is, beyond a shadow of a doubt, because I've got 3 points and I can see how to connect them. It's going to look like the second one. I can also know it's this one. How come? Why is it the second graph and not the first? Yeah, the base, which is 1/3, is between 0 and 1. It's not bigger than 1. So it's also going to look that way for that reason. So if I connect my points, it looks something like that. Domain and range. They don't work any differently here. Domain means if I start from the far left and I walk to the far right, what values do I see? And what do you notice? What do you think the domain might be? Okay, that's a good guess. The difference, though, is that I've got arrows on the end. Do you see those, Sarah? Say, what do you think? Yeah, we actually can continue going left and right, quote unquote, forever. Another way you can think about it is what values could I plug in for x? If you look back at the equation, is there anything that I couldn't do? Well, no. I mean, it might be big numbers or small numbers, but I can plug lots of numbers, kind of any number in for x, and it will be appropriate. So my domain's actually everything. It's -infinity to infinity. Range. Think about walking along the y-axis, right? Climbing the ladder. If you start from the bottom and you climb your way up, what do you think that the range is for this? Yeah, it's 0 to infinity. Should I put a parenthesis? We always put parentheses on infinities. Should I put a parenthesis or a bracket on the 0? Which one? Okay, bracket means I can equal 0. I can't. How do you know? Yeah, it goes right up against it. There's an asymptote there, right? So I don't get to equal 0, but I can get as close as I possibly want. No problem. All right, we're going to try another one that has a little bit more going on. This one does not start out with a table of values for us to fill in, so we get to pick how many and so forth that we choose. My recommendation is that you choose 3. You have to choose at least 2. But 3 usually works pretty well because you get that sort of mirror imaging going on in your table. So here's our equation for the next one. What do you notice happens on this one that's different than the last one? There's a couple of things. It's negative. What else? And it's not a fraction. Very good. So the fact that it's not a fraction means that the basic graph looks like which one of these? The first one. And what do you think is going to happen because there's a negative in front? It's going to flip. How? Is it going to flip down or flip over? Down is actually right. It's going to flip down. So let's check some values because those are our assumptions, what we believe is going to happen, and we can test some values to check it. So typically speaking, I like to let exponents be 0. Zeros are very friendly. And then I would like to choose a point on either side. So -1, 0, 1 is pretty good to pick. If I start with 0, remember, here's the way exponents work. You do exponents before you do the multiplication. So the first thing I do is the 2 to the 0. What is 2 to the 0? 1. And then I have a negative in front, so that makes it -1. Okay? But I got to do the exponents first. So this one is -1. Let's do f of 0 next. I'm sorry, f of 1 next. Again, you start with the exponent. What is 2 to the 1? 2. And then with the negative in front makes it a -2. And the third one, -1. So if I put a -1 in here, what is 2 to the -1? 1/2. It's 1/2. Remember, negative exponents flip fractions, okay? So we do a reciprocal. The reciprocal of 2 would be 1/2. And then I have the negative at the beginning. So I have -1/2 here. All right, so let me plot those points. I have 0, -1. I have 1, -2. And -1, -1/2. And where do I have an asymptote if I want to draw it? Yeah, well, at the x-axis, which would include the point is 0, 0. Yeah. And we would connect the dots, so to speak, to look something like that. What's the domain? Say it louder for me, Trey. -infinity to infinity. That's right, McKaylee. Yeah, far left to far right. General rule of thumb, the domain on exponential functions is always -infinity to infinity. Unless like it's a context kind of, word problem and it doesn't make sense to talk about it that way or something. But these are always -infinity to infinity. How about the range? Bottoms up, right? Start at the bottom. -infinity to 0, exactly. So that's like flipped because the graph flipped over from the last one, right? So that's why the range flipped as well. All right, any questions on that one? Okay, we have one more graph. So far, you've seen what happens when we flip things over. You've seen what happens when you have a value bigger than 1 and a value between 0 and 1. So now we're going to do one that has both of those features. Oh, there's a typo on this one. I didn't get it in there, or maybe it's hiding behind my text. That's what the value should be. So both of those features, it's got the 1/2 and it's got the negative, but it also has at the end a +2. So when we did transformations of functions and we added and subtracted values onto the ends of things, how did that change our graph? Do you remember? In this case, it moved it up because it's +2. So if you add or subtract on the end, it takes the whole graph and moves it up or down. So how's this one going to move? It's going to move up 2, and that's actually really useful to know because it allows me to draw the horizontal asymptote in, because it is different now than the y-axis or than the x-axis. I don't want to draw this thing getting close to the x-axis. That's not appropriate. This has been shifted up. I'm still going to do my table of values, and they're still going to fall in that upper range or that lower range, but it's going to look a little bit different because the asymptote moved. So let's give it a try on some values. Okay, Even so, it's still very friendly to choose -1, 0, and 1 because the exponent's still just x. Okay, so if I plug in 0, what is 1/2 to the 0? 1. With the negative in front makes it a -1, and then plus the 2 at the end makes it a +1. So this one's 1. Let's try f of 1. Okay, what is 1/2 to the 1? 1/2. With the negative in front makes it a -1/2. And then what is -1/2 plus 2? What was that? Yeah, 1.5 or 1.5? I'll do 1.5. It's positive, right? Because the 2's positive. Good. Last one is the -1. So I have -1/2 to the -1 plus 2. So what is 1/2 to the -1? 2. With the negative in front makes it a -2. Plus the 2 at the end makes it actually get 0. Yeah. Okay, cool. So we're going to plot these. I have -1, 0. It's here. I have 0, 1. That's here. And I have 1, 1.5, which would be here. And if I connect those, the question is, does it in fact look like it was flipped over and then raised up like 2 units? Yeah, it does. It's exactly what it looks like. So what's the domain? Yeah, I'm not trying to trick you up. I'm really not. But it is still just -infinity to infinity. None of that changed. The range did.
Will the domain always be -infinity?
Yep. It will. What about the range, though? It will not always stay the same. Yeah, this one's -infinity to 2. Parentheses on both. Good job. Good job. Okay, if you have a calculator, grab it out. Doesn't matter if it's graphing or not. We're not graphing. We're just using a calculator. If you don't have a calculator, I'll let you use your phone for the next, 3 minutes to do this. That's fine. Make sure you can put your phone in scientific notation. I want to make sure that you understand how to approximate with your calculator because you're going to absolutely need it on the application problems without question. You're not going to be able to do this by hand, okay? So these are some just random ones for us to try. If you have your calculator with you, I'm going to have you type in 3.5. That was not in here anymore. Raised to the 1.6. So for some of you, the button looks like you have a button like this. Call it a caret. I've used that word in here before. And you would do like this. Some of you have a button that looks like y to the x. Depends on the type of calculator you have. You'll press that one. So you'd push, usually you push the 3.5 and then you hit the y to the x button and then you push the 1.6. So it kind of looks like this. Just notationally. And we're approximating here to the nearest thousandth. What does thousandth mean?
3 decimal places.
Yeah, 3 decimal places. Cool. All right, so on the first one, if you type in your calculator 3.5 and raise that to the 1.6, what do you get approximately? Okay. If you are getting something different than that, let me know right now and we can see what's going on with your calculator. Is that okay with everyone? Fabulous. On the next one, it looks a little bit more difficult to enter. If you are in fact using like a TI-84 type calculator, I would enter it as 5/7 like this. And then you can do your caret. And you can still do -0.65. Works just fine. If you want, another thing you could do is you could hit 5/7 and hit enter. And then raise that to this -6.5 so you don't have to worry about parentheses. Another option. What is the approximation for this value? Do you guys have it?
1.24.
Yes, indeed. How about the next one? The next one has something interesting that we have not talked about in it. What's different about actually the next two? There's an E. So let me tell you what E is. E is irrational. That doesn't mean it's crazy. It's irrational, as in it's not a ratio of numbers. It's approximately 2.718. That would be a three decimal expansion for it. And it's in your calculator. Like there is actually a button in your calculator that says E. It might be associated with a button that says LN. Okay? So you literally type the E in just like the others, and you do the caret, and then this was negative 0.35. Okay, so you're raising this irrational 2.718 number to a power. But please don't type in 2.718. You will lose accuracy and your decimals won't turn out right. So what is e to the negative 0.35? I have 0.705. Is that what you have? Okay, just checking.
So do you want us to round the last decimal?
Yes, you'll round the final decimal up or leave it alone if it doesn't round up. Exactly.
I have 7 point. And then when I place the parentheses,
It's doing scientific notation at the end. Just got times 10 to the negative 1. I think your mode could change, probably. Yeah, just change it into regular mode. Yeah. Anybody else? So Karen's calculator was in scientific notation mode. Is anybody else not getting this 0.705? Okay, fabulous. One more time. 75 e to the negative or to the positive 0.5. What do you have? My number is quite smaller than that. What do you have, Devin?
275 ln.
No, not ln. Make sure you use the e. Yeah. What'd you get? Okay. I probably had a typo when I typed it in. No problem. Okay, so 123.654. Thank you, Sarah. All right, cool. All right, any questions on these? Okay, pretty simple. I'm just entering numbers in the calculator, but the reason I'm doing it is because we're going to have word problems. So here's what we're going to do. I'm going to do one word problem, Trey. One word problem, and I'm going to finish up the word problems on a separate video for you guys to watch, okay? Because they're very similar, but I want to make sure I get your pictures of your sheets before you leave today. Just start signing sheets. So we have the radioactive substance uranium-240. It has a half-life of 14 hours. The amount present in grams of this substance after T hours is given by the equation A of T equals 3,200, 1/2 raised to the T over 14. And you see the over 14 is coming from that 14 hours. Okay, so I'm not making you create that. They're giving you that, but that's where it's coming from. So jot that down. Yeah, notice this comment at the bottom here. Every problem you do is going to tell you on these how to round, and it's not always going to be to the same thing. So this one specifically says to the nearest gram, which means it'll be a whole number. okay? I mean, we're looking for a whole number answer when we're doing this particular problem. Some of the others might be looking for it to be 1/10 of a gram, or you know, the nearest seconds instead of the nearest millisecond, or I mean, they're going to describe to you how they want your answer to be. Okay. Part A says, find the initial sample amount. What does that mean? What does initial sample amount mean? The amount you started with, the original amount. Good. Okay, so we've got to make sure we understand the language that they're using first. They're talking about how did it begin. So if you were at the beginning of this, you know, experiment or whatever, what value is t? It's 0. Time equals 0 is when we start. Right? Like when you guys count your age, you count from the time you were born. There is a starting point, right? Same thing with this. This experiment that we're counting started at time 0. So what I'm asked to actually find is a of 0. So I'm going to plug in the number 0. You can use your calculator to plug in the number. On this particular one, you can probably do this one without it. The next one you probably can't. But on this one you probably could. So let's just talk through it real quick. What is 0 divided by 14, the little exponent? That's 0. What is 1/2 to the 0? 1. And then what is 1 times the 3200? 3200. So there is an initial amount that is 3200 grams. And if you didn't feel comfortable with me going through all the details, your calculator, that's why we went through this whole problem over here, can help you with that. In fact, it's going to need to help you with that on the next problem. So the next part of this problem says, how much remains after 40 hours? Well, we want to make sure that the t is measured the way we're given the information, and it is. T is in hours. So what would we do to find how much remains after 40 hours? Yeah, I'll evaluate at the value 40. So it'd be 3200 times 1/2 raised to the 40 over 14. Here's the catch, and this is part of why I wanted to do this problem, is because I want you to be really careful. Your calculator needs to know that all of that is the exponent, and some of your calculators require you to put parentheses around that to make that happen. Sometimes the calculator thinks that you mean raise it to the power 40 and then divide everything you just got by 14, which is not the same thing. So be really careful. Make sure you know your calculator and whether it needs those parentheses or not. And if I do this one and I raise it, or I round it to the nearest whole gram, what do you guys get?
442.
442 is right. Good job, Megan. And again, it's grams. 442 grams. Okay, I have 3 more applications. They're super similar to this. I'm going to post a second separate video with that in it, okay? So that way you'll know exactly what you're looking for. You're looking for probably a 10-minute video, and then you'll be able to finish up the work, and I will get that posted before I leave campus today. So you will have that available before you're done with some of your other classes today too.